Questions 21 to 25 on the 2005 grade 12 AMC 12A. How many ordered triples of integers a, b, c with a greater than or equal to 2, b greater than or equal to 1, and c greater than or equal to 0 satisfy both log of b to the base a is equal to c to the power of 2005 and a plus b plus c is equal to 2005. So we have this criteria for our a, b, and c. And I've got the log of b to the base a is equal to c to the power of 2005, and a plus b plus c has to be equal to 2005. So let's begin. I'm going to first concentrate on c. And since c is greater than or equal to 0 and it's an integer, I will start with c equal to 0. And let's see what we get. If c is equal to 0, this becomes the log of b to the base a of 0 to the power of 2005, which is of course just 0. So then this becomes a to the power of 0 is equal to b, and therefore a to the power of 0 is 1, and therefore b is equal to 1. So now we have to use this formula to get a value for a. A plus b, well, b we just established was 1, c we set as 0, and that's 2005, and therefore a is equal to 2004. So we have our first ordered triple a, b, c. We've got 2004 for a, 1 for b, and 0 for c. All right. So the answer is obviously not 0, so we can cross one thing out. Now let's set c equal to 1 and see what we get. If c is equal to 1, then we will have the log of b to the base a is equal to 1 to the power of 2005, and that's just 1. So therefore a to the power of 1 is equal to b, and therefore a is equal to b. So if a is equal to b, and we go back and use our formula to figure out the values of a, b, and c, we will get a plus b plus c, well, c we established was 1, is equal to 2005. All right? And that gives me a plus b is equal to 2004. And therefore, since a is equal to b, this gives me 2a is equal to 2004. And therefore, a is equal to 1002. And b is also equal to 1002 since a is equal to b. So my second ordered triple that I have discovered is 1002, 1002, and 1 for c. So the answer obviously can't be 1 since I've got 2 so far. All right, let's keep going here. Let's try c equal to 2. Let's see what happens. If c is equal to 2, we have log of b to the base a, 2 to the power of 2005. So that means a to the power of 2 to the power of 2005 is equal to b. Well, that's going to be a very, very big number. And even if you have the smallest possible a, which is 2, that's the smallest possible a, 2 to the power of 2 to the power of 2005 is going to be a huge number. B will be a very, very large number, and there's no way that we'll be able to satisfy this with integers. So that's it. There's only 2 ordered triples. We got them right here and here, and therefore number 21, the answer is C. A rectangular box P is inscribed in a sphere of radius r. The surface area of P is 384, and the sum of the lengths of its 12 edges is 112. What is r? So first let's draw a box, a very basic box here, and we will try to figure out as much as we can. We will try. So let's start labeling this box, and we'll concentrate on the sphere a little bit later. Well, obviously length, width, height, correct? And let's see, what kind of information did they give us? Surface area is 384. All right, well, what is the surface area in terms of length, height, and width? It's 2 times length times width plus 2 times height times width plus 2 times height times length, right? That's entirely from the diagram. I certainly didn't memorize that. And if we do this, we obviously can factor out a 2. You get LW plus HW plus HL is equal to 384. And if you divide through, you'll get 192 for LW plus HW plus HL. Okay, that's the first clue they give us. Then the next one is the sum of the lengths of the edges is 112. All right, 112 is equal to, well, the L looks like it will appear 4 times. So that's 4L. Sum of the lengths of the edges. The height also appears 4 times right there. So we got 4H. And in a very similar way, the width will appear 4 times in terms of lengths of edges. So there you go. If you divide through by 4, this will give you 28 is equal to L plus H plus W. Okay? So this is the initial setup of the question. Now let's talk about the sphere. There's going to be a sphere that's going to be placed in this diagram so that the rectangular box sits entirely inside of it. You know, something like that, right? And I'm not going to attempt to draw the sphere. I just want you to be convinced that when you do inscribe this box inside the sphere, the vertices will touch this sphere. Okay? That's really the only thing you really need to know. The vertices of that box will touch the sphere. So if you draw a line from the very center of this box, so let's say that's there, all the way to one of the vertices, that will represent, I think you already know what I'm going to say, the radius of the sphere. Correct? That is really the main thing I want you to understand in this question. So any time you draw a line from the center of that box to a vertice like that, it will represent the radius. Okay? So I'm just going to concentrate on one of these. So I drew a line from the center of the box to one of the vertices, and that represents the radius, r. And then what I'm going to do is I'm going to draw a line to establish some sort of a relationship between r and our sides of the boxes. So I'll draw a line from the center all the way to the base there. Okay? And then a line from the edge of the cube, or box I should say, to meet the other line. And that is the triangle that will help me figure out what is the relationship. And this is of course a right angle, so I'll draw in that right angle. All right? So I hope you followed what I did there. That red line represents the radius r. And then these green lines, I have to start figuring out what they represent. Now this one here, from here to here, that one's pretty straightforward. That is just half the height, h over 2. All right? So that one is the easy one to figure out. But this one is a little bit more complicated. Not extremely complicated, but just a little bit more. Because in order to figure out that one, I have to do another triangle. And that other triangle is from the base to right here, the midpoint of that. All right? Now to avoid making this diagram messy, I will draw that triangle again, but I'll draw it here. So I'll draw it here. Now, let me label, it's this triangle that I have drawn out. It looks like a little bit on a slant there, but that's just the way the box has been drawn. But if you look at it from a bird's eye point of view, it will be exactly like this. Okay? Now, this part here, from here to here, is just W over 2. Okay? And this part here is just L over 2. So now, using Pythagoras, I will try to figure out that hypotenuse. Okay? And that hypotenuse, you can label it anything. We can call it Z. Squared is equal to W over 2 squared plus L over 2 squared. And therefore, Z will be W squared over 4 plus L squared over 4, all under the square root sign. Okay? So that's what this is right here. And we'll just call that Z instead of putting this big long thing. So now we have it. We are very, very close to figuring this whole thing out. Now I will concentrate on this triangle right here and use Pythagoras to get a relationship between R and all the other sides. So we got R squared is equal to H over 2 squared plus Z squared. Correct? So R squared is therefore equal to H squared over 4, and Z squared is W squared over 4 plus L squared over 4, like that. And therefore, this is going to be H squared plus W squared plus L squared all over 4. And if you take the square root of both sides, you'll get R is equal to the square root of H squared plus W squared plus L squared all over 2. Okay? So, where do we go from here? Well, we have to go back and utilize these two equations and come up with what this equals right here. Now, at first that might seem like a daunting task, but it's actually pretty straightforward, and I'll explain why. If you've done a lot of algebra in your time, then you'll understand and you'll even recognize this. If you take H plus W plus L and you square it, you'll be able to figure out this whole question. Let's do that. Well, it's H plus W plus L all squared, correct? Nothing fancy. There's no tricks in this one, I promise. Well, H plus W plus L is right here. So if that's squared, it'd be 28 squared. And then now I'm just going to expand this. So I got H squared plus 2HW plus L plus W plus L squared. So it'll be W squared plus 2WL plus L squared. All right. And then let's see here, 28 squared. Can I collect any like terms here? H squared plus W squared plus L squared. And then what else do I got? 2HW plus 2HL plus 2WL. Okay, I've got a lot here. This one right here, we already figured out. It's right up here. LW plus HW plus HL is 192. So if we were to factor out the 2, we'd be able to get exactly what was up there. So you see, without any tricks, we were able to get this. There's nothing that you have to add and subtract, and sometimes, you have to do those tricks. Nothing of that nature. This is 784, and therefore 784 minus 384 is equal to H squared plus W squared plus L squared. And that is equal to 400. So we get a nice even number. And there you go, we're done. Now we just take this, substitute it up here, right here. So R is equal to the square root of 400 over 2 Square root of 400 is 20 divided by 2, and therefore 10. And there you go. That's the answer. That's what they were looking for, the radius. What is r? And the answer is 10. So 22, the answer is B. Two distinct numbers a and b are chosen randomly from the set 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, all the way up until 2 to the power of 25. What is the probability that log of b to the base a, is an integer? All right, so we've got this set 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so on, right? All the way until you get to 2 to the power of 25. And you're going to choose two of these, a and b. One will be representing a, one will represent b. So first, because it's a probability question, as always, I'm going to figure out the denominator. The denominator is the total possible choices. We'll have to choose two. All right, well, for my first number, I've got 25 possible choices. And for my second number, I'll have 24. So 25 times 24 is the denominator. That's basically the total number of possibilities. The numerator is what we're interested in based on the criteria in the question. And they're saying that when you choose a and b, the log of b to the base a will be an integer. Okay, so how can that happen? All right, well, let's think about this. Let's say you chose these two, the first two, this representing b and this representing a. Well, this would therefore become the log of 2 to the power of 2 to the base 2. And like log rules, this 2 comes out front, and then you're just left with this. And this is equal to 1. So this just becomes 2 times 1, which is 2. Is this an integer? Yes. All right, can I establish any kind of criteria? I think so. I think one of the criteria is that b has to be greater than a. Otherwise, this is not going to be an integer. Okay. Any other criteria here? Let me try one more here to figure out any other criteria. I'm going to choose, let's see here. For b, I'll choose 2 to the power of 6. And for a, I'll choose 2 to the power of 3. Okay? Both of them, of course, are from that list. Now, if I do that, watch what happens. We got 2 to the power of 3. 2 to the power of 6 is essentially 2 to the power of 3 squared. So in a very similar way, you put the 2 out front, and then you get this. And again, this gives you a result of 1, and therefore this becomes an integer. Okay, I got it. So b has to be greater than a, and b also has to be a to the power of n. It has to be some sort of multiple, but multiple is not the best use of a term to describe this. B has to be a to the power of n, so a exponent. You see what I mean? It has to be raised to a certain power. So b basically has to be a to the power of some number. Okay, I think I can figure this out with a table with my two criteria. So I've got a, I've got b, and let me write my two criteria here. B has to be greater than a, and b has to be a to some power of n. Okay? All right, let's make this table, see what happens. Starting with a 2 to the power of 1. Well, I've got many choices here. 2 to the power of 2, 2 to the power of 3, all the way up till 2 to the power of 25. So there's a lot of choices for this one. So the number of choices I'll write here. That looks like 24. How about if I have a to the power of 2? Well, at this point, I can only use 2 to the power of 4, 2 to the power of 6, 2 to the power of 8, and so on, all the way up until 2 to the power of 24, correct? Because remember, a to the power of something has to be equal to b. All right. So if that's the case, this gives me 11. 2 to the power of 3. How many ways can I do this? 2 to the power of 6, 2 to the power of 9, 12, all the way up until 2 to the power of 24. Like that. And that gives me 7. 2 to the power of 4, I get 2 to the power of 8, 2 to the power of 12, all the way up until 2 to the power of 24. And that is 5 of them. 16, 20, yeah. 2 to the power of 5, 2 to the power of 10, 2 to the power of 15, 2 to the power of 20, and 2 to the power of 25. So that's 4. All right, I think you're getting the hang of this. 2 to the power of 6, 12, 2 to the power of 18, and 2 to the power of 24. That's 3. 2 to the power of 7, 2 to the power of 14, and 2 to the power of 21 for choices for B. 2 to the power of 8, 2 to the power of 16, and 2 to the power of 24. That's 2. All right. 2 to the power of 9, I think just 2 to the power of 18, so only 1 there. 2 to the power of 10, just 2 to the power of 20, that's 1. 2 to the power of 11, only 2 to the power of 22, that's 1. 2 to the power of 12 is 2 to the power of 24 for B, and that's 1. 2 to the power of 13, I think that's it. I can't choose anything because we don't have a 2 to the power of 26. It only goes up to the power of 25. So that's it. Let's add all these up. 24 plus 11 plus 7 plus 5 plus 4. 3, 2, 2, 1, 1, 1, 1 is 62. All right. We got it. 62 is my numerator. There you go. That's my probability. Well, we obviously have to figure this out in terms of lowest terms. So 62, 25 times 24 is 600. So 62 over 600, 31 over 300, I believe, is lowest terms. And therefore, number 23, the answer is B. Let P at x equal to x minus 1, x minus 2, and x minus 3, all multiplied. For how many polynomials q to the x does there exist a polynomial r to the x of degree 3 such that p to the q to the x is equal to p to the x times r to the x? P to the q to the x is equal to p to the x times r to the x. That's what they've given us in the question. Well, p to the x, obviously, it's a third degree polynomial. If you multiply all that out, there'll be some x to the third in there. And then r to the x, they tell you is a third degree polynomial. So p to the x times r to the x will be some sixth degree polynomial of some kind. Now, that means that q to the x must be a second degree polynomial, x squared something. Because if you're going to put q to the x into p, remember p to the x is a third degree, right? It's a third degree polynomial, something, dot, dot, dot. But if you put a second degree polynomial in there, which is what q must be, this will become x squared to the power of 3, which is x to the power of 6, matching what it needs to be. So this is a second degree polynomial, so that means q to the x must be of this form. It must be ax squared plus bx plus c, a second degree polynomial. All right, so that's the first part of the question. Now we are going to use this and this, really the only two equations they give us, and work with this. So we have p to the q to the x is equal to q to the x minus 1, right? I'm just using this one right here. No tricks, just exactly what you always do in these kinds of questions. Q to the x minus 2, and then q to the x minus 3. All right? And they tell you that it's equal to this. P to the x times r to the x. P to the x times r to the x, like that. Okay, let's move this up. Well, p to the x was given as x minus 1 in the question stem, x minus 2, and x minus 3, like that. And of course, we have to multiply that by r to the x. All right, so that's the setup of the question so far. No tricks, nothing. Now, we are going to obviously conclude that the roots of this will happen when q to the x is equal to 1 or 2 or 3. So I am interested in q to the 1. I am interested in q to the 2 because this is going to help me, and q to the 3. Okay, so let's do these individually. Q to the 1 basically becomes q to the 1 minus 1, like that, q to the 1 minus 2, and q to the 1 minus 3. And if you're putting in q to the 1, that means you have set x as 1. And if x is 1, then this will become 0. 1 minus 1 is 0. Okay? So instead of putting that like that, I'll just put p to the 1 times r to the 1, and that is equal to 0. Correct? X was set as 1 in this equation. And p to the x is this, and if you put x as 1, this whole thing becomes 0. In a very similar way, let's do the next one. Q to the 2 minus 1, q to the 2 minus 2, and q to the 2 minus 3. That's equal to p to the 2 times r to the 2. And again, since you have x minus 2 and we set x equal to 2, this becomes 0. And in a very similar way, we'll do q to the 3 minus 1, q to the 3 minus 2, and q to the 3 minus 3, like that. So this is p to the 3 times r to the 3, and that is equal to 0 again. All right? So what have we concluded with this? Well, since this is equal to 0, and this is equal to 0, and that is equal to 0, that means that q to the 1 must be 1, or it could be 2, or it could be 3. Any one of those would satisfy this equation, the first one right here. All right? From the second one, which is here, we know that q to the 2 could be 1, or q to the 2 could be 2, or q to the 2 could be 3. Entirely from this, because they're all equal to 0. It all equals 0. And then from the third one, in a very similar way, we can conclude that q to the 3 is equal to 1, or q to the 3 is equal to 2, or q to the 3 is equal to 3. All right? So this is our conclusion. Now, recall we had set q to the x equal to a second degree polynomial, ax squared plus bx plus c, which is exactly what it will be. And we have all these possibilities. For example, if q to the 1 is equal to 1, this first guy right here, that would basically mean, if you use this, that 1 is equal to a plus b plus c, right? If you put 1 as x, that is what this becomes. All right? So how about you have q to the 1 is equal to 2, this one right here. Well, that would give me 2 is equal to a plus b plus c. And if q to the 1 is equal to 3, and I use this formula, I would get 3 is equal to a plus b plus c. All right? So that takes care of those guys. And I'll do the other 6, starting with this one. If q to the 2 is equal to 1, and I use that formula, I get 1 is equal to 4a plus 2b plus c. If q to the 2 is equal to 2, then I will get 2 is equal to 4a plus 2b plus c. And if q to the 2 is equal to 3, like that, then I get 3 is equal to 4a plus 2b plus c. And in a very similar way, these guys using this one will give the following. We will get, if q to the 3 is equal to 1, you have 1 is equal to 9a plus 3b plus c. And if q to the 3 is equal to 2, you get 2 is equal to 9a plus 3b plus c. And finally, if q to the 3 is equal to 3, we get 3 is equal to 9a plus 3b plus c. All right. Okay. Well, trust me, we're getting somewhere. We're making progress. Well, that means that we've got 9 different scenarios, correct? 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means for q to the 1, I've got 3 different possibilities. 1, 2, 3. For q to the 2, I've got 3 different possibilities. 1, 2, 3. And for q to the 3, I've got 3 different possibilities. 1, 2, 3. So for each of these, I can choose one of 3 possible. So the total is 3 times 3 times 3, which is 27 possible ways of making this polynomial. All right? So you go back and you choose 27 and you move on, correct? No, that's why this question is so difficult. And most people, if they got that far, they deserve some credit, right? But if they choose 27, unfortunately, they're wrong. Why are they wrong? Did I do anything incorrect in this question? Well, so far, no. The only thing is that of these 27 possible polynomials that we can create, not all of them are going to have a second degree quadratic. Some of them will be first degree, and then some of them will be 0 degree. So we have to, unfortunately, in a painstaking way, go through all of them. Now, maybe you have a shortcut, and I'm sure that there is. So I'm not going to go through all 27. I'm just going to go through the 5 that are not second degree polynomials. And those are as follows. Some of these 27 will not be quadratics, namely, the first one is when q to the 1 is equal to 1, q to the 2 is equal to 1, and q to the 3 is equal to 1. So going back, what you've done is you've chosen basically q to the 1 is equal to 1, you've chosen this guy, q to the 2 is equal to 1, and q to the 3 is equal to 1. You've chosen those 3 as your values for q1, q2, and q3. If you do that, and you do all the math, you will get a polynomial of this form, qx equals 1. So that's a 0 degree polynomial, right? It's just a straight line. So that is one exception. The other exception is when q to the 1 is equal to 2, q to the 2 is equal to 2, and q to the 3 is equal to 2. If you do that, you get q to the x is equal to 2. The third one is when q to the 1 is equal to 3, q to the 2 is equal to 3, and q to the 3 is equal to 3. That gives q to the x is equal to 3. Again, not a quadratic. The fourth one is when q to the 1 is equal to 1, q to the 2 is equal to 2, and q to the 3 is equal to 3. If you do that, you'll get q to the x is equal to x, which is a first degree polynomial, x to the 1. And finally, the fifth one that doesn't give a quadratic is when you have q to the 1 is equal to 3, q to the 2 is equal to 2, and q to the 3 is equal to 1. This gives q to the x is equal to 4 minus x. So these 5 you have to subtract from our 27. And if you do that, you get 22. and 22 is the answer to this question. So number 24 is 22, and therefore that is choice B. Let S be the set of all points with coordinates x, y, z, where x, y, and z are each chosen from the set 0, 2, 1. 0, 1, 2. How many equilateral triangles have all their vertices in S? So the best way to do this is with a diagram. So here's our diagram. We've drawn an xy plane, xyz plane. And basically you've got, for x, y, and z, it can be either 0, 1, or 2. So you can only choose between those three numbers as a possible coordinates. And if you do that, you will be able to see that you will create, first and foremost, unit cubes where the vertices are only going to be within one of each other. And that's if you just chose this one or if you just chose those two. First, we'll just concentrate on the unit cubes. So one unit cube gives several equilateral triangles. And this red illustrates one such equilateral triangle. You'll notice that it has a length from there to there for each of its edges. And since the length from here to here is 1, we can easily figure out through Pythagoras that the edge is root 2. So it gives equilateral triangles of side length root 2. Now, how many does it give? If you have a unit cube, how many? Well, each of these vertices of the unit cube will produce 1. And how many vertices do we have in a cube? We have 1, 2, 3, 4, 5, 6, 7, 8, correct? So we get 8. Okay? But how many unit cubes? The whole thing is 2 by 2 by 2. So that's 8, right? So if you have a cube of volume 8, that is 8 unit cubes. And since each unit cubes gives 8 equilateral triangles, 8 unit cubes will give 8 times 8, 64 equilateral triangles. All right? But that's just the first part of the question. We also have to take into consideration when you have a full cube where the whole sides are of length 2 each. And the green triangle represents one such equilateral triangle. At this time, we are now drawing side lengths that are much longer, double the length. So instead of root 2, these now have side length 2 root 2. All right? Now, how many of those green triangles can I make? In a very similar way, each of these vertices will produce one such triangle. So there's 8 that will be produced by the big cube. Also, we have large equilateral triangles of side length 2 root 2, 1 per vertice. So we have an additional 8 large equilateral triangles. So we have 64 and 8. So that means 64 plus 8, we have a total of 72. So 72 is our total. 72 is one of the answers. But perhaps we can get a few more. Let's see. Now, what if I chose triangles like this, where they are connected by the midpoints of sides? By connecting midpoints of non-adjacent, non-parallel edges, an additional 8 equilateral triangles can be made, as shown. So we have 8 here, we had 72 here, 8 plus 72 is 80. So the grand total is 80, and therefore number 25 The answer is C.